Good morning, everybody. We are discussing, first of all, the vapor compression refrigeration system with various type of variation of different stages of the refrigeration system. At present, we are discussing this in such a way that our compression process is the beginning. At the beginning of the compression process starts from the vapor vapor saturation line. That is stage number 1 is situated on the vapor saturation line, and thus, as we know, as we have discussed and finalized, that this as we have discussed and explained, as I have explained, that this compression system is creating problem for myself. We have already discussed, if we, as our we have 4 stages in vapor compression refrigeration system. One is compression stage, where the refrigerated vapor stage is compressed from low to high pressure and low to high temperature of the system. Next, that compressed vapor at high temperature and pressure entered into the condenser, where it is cooled and converted into liquid refrigerant at high pressure. And it is after the end of condensation, we said that is the stage number 3. We send this liquid refrigerant under high temperature pressure to an expander or throttling device, which cools it to the lower temperature and volume is expanded. Thus, pressure is reduced to the lower pressure of the system, and this process is finished at the stage 4, which is the inlet of the evaporation system. So, at evaporator, which is the stage converted the vapor refrigerant from liquid to vapor by absorbing the latent heat from the surrounding of these coils through which this vapor is moving. So our space inside the refrigerator, which is being cooled, so that is this latent heat for evaporation of the refrigerant is being absorbed from the surrounding of the coils of the evaporator itself. Now, this happens like this: as the compressor receives this vaporized refrigerant at vapor refrigeration line. So after compression, it reaches the superheated state, which, because it is goes to the superheated state itself. As we know, this portion is this next line 10 is the vapor compression line. This line 1, this point 1 is on the vapor saturated vapor line. So after the compression, it reaches the point after the compression is finished, it reaches the point 2, which is in superheated region. Now, what is superheated? If a certain fluid, in vaporized stage is heated more than its boiling point, it is called superheated position. So all the points over this in this diagram over this vapor saturation line is that it is totally vapor is totally saturated and in their boiling point itself. But if it is beyond this line, the vapor will remain in vaporized state, but it is additional heat is imparted to it, and it is becomes superheated and carries the temperature which is higher than the boiling point of the vapor constant itself. So we have seen the point 2 is higher than, that is equivalent to the temperature T2 is higher than the higher temperature of our state, which is 299. It is for this type of problem. So in the condensation process start from 2 and reaches at the point 3, but a part of it is from superheated position where it is not isothermal but releases heat and reduces the temperature, and it reaches at the point 2 dash, which is on the vapor saturated vapor line. Then it is released further heat from 2 to 2 dash to as an isothermal process and reaches to wet saturated vapor line 3 itself. This is the process of the process of keeping the vapor represented after refrigeration evaporated at the vapor finishing at a vapor saturated vapor line, which has some certain problem like this because its evaporation state is more on 4:1 is higher than the earlier stages where 0.1 is in the wet dry region of the phase cycle. But now, as the refrigeration length is more than that, so it is creating more refrigerating effect. And it is, but at the same time, it is also creating more compressive, more work to finish the compression process. Thus, as a whole, COP is not increasing for this particular type of particular application itself. Still, let us go through another problem to finish this type of application. What we given here, it is a water-cooled R12 refrigerant. Using R12 refrigerant works on condensing and evaporating temperature of 26 degrees centigrade and 2 degrees centigrade. Condensing temperature is 26 degrees centigrade. It is we can consider it is the higher limit of temperature of the system, and at evaporating is going on at 2 degrees centigrade, means it is the lower heating temperature of our particular system itself. So that is equal to T2 and this is equal to T1. T2 is equal to T3 and T1 is equal to T4 itself. So here what we do, T2 dash here, as it is in superheated region. So let me go through the problem. The vapor leaves the evaporator saturated with dry, which means it is on the dry saturated vapor line, and then average output of cold water is 100 kg per hour cooled from 26 degree to 6 degrees centigrade. So we are using this refrigeration system to cool a certain amount of cold water from 10 kg per hour, which is flowing at a rate of 10 kg per hour, and it is cooled from 26 degrees centigrade to 6 degrees centigrade. So the temperature of this cooled water is initially equal to our condensing temperature. Condensing temperature is 26 degrees, but it is cooled up to 60 degrees, not up to 2 degrees. That is which is the evaporating temperature. Now, it is another problem is a 20% of the useful heat into the condenser cooler, and the volumetric efficiency of the compressor as 80%, and mechanical efficiency of the compressor and the electric motor is 25% and 95% respectively. So we are using two more efficiencies. One is volumetric efficiency, means full volume it cannot be compressed. So 100% compression, then V1 by V2 is equal to 100%, means total reduction in pressure, volume. but it's not like this. It is 80% of it. And the mechanical efficiency of the compressor means that is not converting full input with power into the compression process, but up to 80%. And motor current is also not fully utilized, which is up to 90%, 95%. So we have to use this thing to know what is the volumetric displacement of the compressor itself and the power of the motor itself. And the data are given here. So volumetric efficiency means how much if it is absorbed or it is compressed, the total volume of the refrigerant is here in the fluid. So it is supposed to be 100% efficient. Of compression is supposed to be 100% efficient. But as it is told, 80% only means it can compress 80% of this full volume of the refrigerant, because others remaining 20% may be wasted to start leakage or leakage in between the walls of the compression and the cylinder or some other reason. And the electric motor is 85% means electric motor power is 95% means the power of the motor is not cannot be fully utilized to run the compressor itself. So we have to think, we have to find only 2 points: volumetric displacement, but at the point power of the motor. But in this, to make it, we have to know all the heat content of all 4 points: 1, 2, 3, 4. That is H1, H2, H3, and H4 itself. And with the available data, which shows us the temperature as per the condenser temperature and evaporator temperature, the corresponding pressure is 6.69 bar and 3.29 bar. And here T2 dash, which is equal to T3, as per the figure below. Here T2 dash is equal to T3, means here this is T2 dash and this is equal to T3, which is given as 26 degrees centigrade, means as you have to convert it to degree Kelvin to 99 K. And T1, temperature of the evaporator is given is T1 here, which is equal to T4 itself. It is only 2 degrees centigrade, that is 2 plus 273 is equal to 275.2 degree Kelvin itself. And water value, the weight of water, circulated water is 100 kg per hour itself. And its temperature is also same. Its higher temperature from where it is supposed to be cooled is equal to 99 degree Kelvin, and lower temperature up to which it will be cooled, it is only 279 degree Kelvin itself. The efficiency is 80% of the volumetric efficiency 80%. Motor efficiency is 85%. And motor efficiency is 95%, and now M1 is 85. See, 85. Mechanical efficiency is, that is 85%. I forgot. The mechanical efficiency is 85%, and motor efficiency is 95%. Now we have to find out from the chart what is HF3, which is the enthalpy of the fluid, enthalpy of our refrigerant at fluid stage at the point 3 itself, which means at the fluid stage itself. HF3 is the enthalpy of the refrigerant at point 3 at the exit of the condenser itself, which means it is the liquid enthalpy at higher temperature or condenser temperature, which is given as 6.54. So it is 60.54 itself, not 64, but 60.564 itself. Next, HF1, it is called superfluous data exit, which is the enthalpy of the fluid at stage 1. Stage enthalpy in wet stage, that is given as lower at condenser temperature, that is 2 degrees centigrade. Enthalpy of the fluid will be at 37.95 degree, 37.95 kilojoule per kg. That is 37.95. Next comes H2 dash, which is the enthalpy of the condenser at enthalpy of the refrigerant at the vapor at saturated vapor stage means it at the saturated vapor line, which is that it is condensate. It's supposed to be the condensate temperature, supposed to be corresponding to the condensate temperature of 26 degrees centigrade, and it is on the vapor line in the vapor stage. So enthalpy of vapor stage, that is equal to 198.10. It's 198.10. H1 is the H1, which is also the entropy at the refrigerated state, which is situated exactly on the vapor refrigerant line. So it is supposed to be 188.39 degrees Kelvin, kilojoule per kg. Next comes the entropies. Now, first we have to know entropy at the point of the fluid at the point 2 means now entropy of the fluid at the point 3. What is that point? This is the entropy at the fluid state at the point 3. This is the point itself. Here it is on the wet saturated line. So this entropy will be the entropy of the vapor at condensate temperature on in liquid state, where the refrigerator and the refrigerant on the liquid state. So it is SF3 will be the entropy at liquid state at high condensate temperature. This is the 0.2270. It is given here. And SF1 entropy of the fluid at the point 1 at the point 1 means when the entropy is entropy at the entropy at the point 1 is the fluid state itself, means it is in the evaporator temperature as well as in the evaporator temperature, that is equal to 2 degrees centigrade, as well as where it is situated on the fluid on the wet saturated line, that is also 0.467, 0.1487 itself. Next, we are going to S2 dash, entropy at the point 2 dash, when the 2 dash is the point at the which is situated in the condenser itself, but it is pulled from the superheated point H from the point 2 where the fluid is superheated to the point 2 dash where the fluid is become dry saturated itself. Means this is the entropy of the refrigerant at vapor stage when it is on the dry saturated line as per the condensate temperature. So it is on the vapor line here. It is as per the condensate temperature 26 degrees centigrade. Is the vapor stage, and it will be 0.685, 0.6865 itself. Next, S1, S2. S1 is supposed to be equal to S2 because we are going through a isentropic process. So we know that 1 and 2 is the isentropic process. This entropy remains constant from 1 to 2, as if we are understanding there is no such heat is being transferred through this pipe or transferred or leakage through this pipe here. It's a theoretical concept, but only the additional amount of pressure is being increased from 1 to 2, and enthalpy also due to the addition of the what enthalpy content is increased, with energy content is increased, but no heat transfer is supposed to be take place. So S1 is equal to S2. So S1 we have already calculated. So here S1 is equal to S2 0.6956. Now we know the CP3 is 0.996 is the specific heat of vapor refrigerant 0.996, and CP4, that is specific heat 1.067 kilojoule per kg. CP3 is the coefficient of specific heat at the point 3 here, where the refrigerator vapor state, and CP4 is the specific heat when it is in the totally. It is also in the liquid state, but at the point 4 itself 1.067 0.16 because here the refrigerant is in liquid state and here the refrigerant is in gaseous state itself. No, in both the cases refrigerants are in liquid and CP2 dash is specific heat at 0.674 itself, and CP1 specific heat at the 0.1 itself, and V2 dash is 0.026 meter cube per kg, and V1 is 0.052 meter cube per kg. It's volume at the 0.1 here, and after the compression it becomes volume at the 0.1 here is 0.52 cubic meter per kg, and specific volume at 2 is equal to 0.26 meter cube per kg itself. This is not given, it is available from the TS diagram itself. Now, in for TS and pH diagrams are shown in the figure. The TS and pH diagrams are shown in figure 4.15a and b respectively. This one and this one. Now 20% of the useful heat is lost into the water cooler. It's lost into the water cooler itself. Therefore, the actual heat extracted from the water cooler will be the flow rate of water and multiplied by the specific heat of water, multiplied by the temperature of the water at stage 1 and temperature of water at the stage 2. When higher temperature, 299, and lower temperature of water will 279. That is 6 degrees centigrade, etc. And so it is 20% useful is lost into the water cooler. Just here, there is given 20% of the liquid heat is lost in the water. So in order to calculate the heat lost or heat extracted from the water, we'll have to multiply the heat by a factor 120% or 1.2. So specific, this is the flow of water is given as 100 and CW is 4.178. That is specific heat of water is 4.187 kilojoule per kg degree Kelvin. So it becomes 10,050 kilojoule or 167.5 kilojoule per minute. This is the amount of refrigerating effect we are supposed to create. The amount of effect which we are supposed to create. Now, we know the heat extracted or the net refrigeration per kg of the refrigerant will be what? H1 minus HF3. That is H1 minus HF3 itself. That's we know, although it is not shown in the figure, we assume that H1 is equal to value of the H is a during the expansion there is some heat transfer will take place, but enthalpy it is a constant enthalpy process. No heat content is not rising or reducing. Although during expansion some heat is lost, but that loss is negligible, and so we conclude that this is more or less a constant enthalpy. This is more or less a constant enthalpy process. So HF3, which is the enthalpy of the heat at the fluid state at 0.3, and that will be equal to HF4. So we have already calculated that, and so the heat extracted we have reduced from the chart as 183.39 and HF3 is 60.54. The total refrigerating effect per kg refrigerant is 1.275 kilojoule per kg itself. So the mass flow of refrigerant required is it is the amount of refrigeration required 167.5 divided by 127.75, which is equal to 1.3 kg per minute. So this is the mass flow we have started calculating itself. and the volumetric efficiency of compression will be the uh, the mass flow divided by mass flow multiplied by the specific volume of the unit divided by uh, so, I mean the volumetric efficiency. So volumetric displacement means how much the compression is being displacing for each stroke and how much volume it is compressing for each particular stroke itself. It can be governed by the mass flow refrigerant multiplied by the volumetric the specific volume of the refrigerant divided by the volumetric efficiency. That is, this two is particularly given, and that is 0.8 is 0.85 cubic meter per minute. First of all, next let us find out the temperature at the point T2 is a T2. We have to know first because we have to calculate the COP. So you have to know the first temperature, then the enthalpy at the point two. We know the entropy at the point 2 becomes follows this equation. The entropy at the point 2 is equal to entropy at the point 2 dash plus 2.3 into specific heat of the refrigerant vapor at the point 2 dash multiplied by log T2 divided by T dash means temperature, the temperature of the condenser divided by the specific superheated temperature of the refrigerant, vapor refrigerant. We put the value one by one. This is all we have given, and CP2 is also known to us as log T2 by 299. Log T2 by 299 will be after the simplification, taking the exponential of this term and substitution here, then T2 the superheated vapor becomes 222 plus 1.0936 is equal to 306 degree Kelvin. Next, we can have, as we know now, the temperature at the point 2, we can calculate the enthalpy at the point 2, which is given by H2, which is equal to enthalpy at the point 2 dash plus specific heat of the vapor at the point 2 dash, of the vapor refrigerant at the point 2 dash, which is given as 0.674, and multiplied by temperature at temperature of the vapor on the vapor saturated line minus the superheated temperature itself. This superheated temperature which is 303 and temperature of the vapor at dry saturated line, that is 299. That is given, which will be given as 200.8 kilojoule per kg. Now we got H2 and we know H1. So we know that the work done by the compressor per kg of the refrigerant is the difference between these two enthalpy itself. Means this is the difference between the two heat energies, means that amount of work is being transferred here. So 200.8 is the H2 minus 188.39 into 188.39 is equal to 12.41 kilojoule per kg. And work done per minute is the is supposed to be given by. So the work done is going on. Work done which is required for this to make required in this compression is equal to 12.41 kg per kilojoule per kg. But now, and work done per kg is the should be multiplied per minute should be multiplied by the flow rate of the refrigerant, which we have calculated equal to 1.3, which is the mass flow of refrigerant we have calculated here 1.3 kg per millimeter. So if you put it and multiply it by the the change in enthalpy, which is 12.41, then the work done per minute, which is supposed to be 16.1133 kilojoule per minute. If you can reduce 0.07 kilojoule per second, which is equal to 0.27 kilowatt per second itself. So what is the power required from the compressor itself? This is the power. It is compressor requires to be delivered, and compressor and the motor has 85% efficiency. This is the efficiency of the motor. So if we divide this power to the efficiency, so we get that is the 0.317 kilowatt amount of power is required for the motor to produce. So the power of the motor, this is the mechanical efficiency. Sorry, this is the mechanical efficiency of the compression. So compressor is required to produce 0.317 kilowatt, and the power of the motor, which is supposed to be produced, is which to be divided by the efficiency of the motor, which is 0.95, which is 0.0334 kilowatt. This is to have the answer. So we don't have to calculate COP for this type of problem because it is not required. But here we have to calculate all the enthalpy of all the points H1, H2, H3, H4, and we do have to find out the difference between the H1 and H2, which is the amount of heat being transferred by the compressor. Then we have to multiply this kilojoule per kg